So let's quickly go through the problems in tutorial 3, and I will sketch the solutions for you. So the first problem deals with operators. Well, all of them deal with operators in some sense. The first problem is designed to give you some practice in constructing operators. The second problem is designed to give you some experience with calculating expectation values and so on and so forth. Okay. So the first problem says that the operator SZ that was discussed in class can be diagonalized to yield the eigenvectors plus and minus. These are the eigenkets in the two-dimensional linear vector space. In this basis, work out the operator representation of Sx and Sy, and further, using the orthonormality of the kets, demonstrate the combination relation given here is true. Okay, all right. So this is a fun problem, and there is no detailed derivation that tells you exactly what is Sx and what is Sy. Basically, we're going to guess the form of Sx and Sy just the way we guessed the forms of Sz and the identity operator at class. Okay, so what is given to us is the fact that these kets, which are the eigenkets of the Sz operator, form a complete basis in this two-dimensional linear vector space, which is an obvious statement because Sz, as you know, is a Hermitian operator. In class, we discussed the operator form of two operators in this two-dimensional linear vector space. The identity operator, okay, this actually stems from the fact that this is a complete basis. This is the definition of the identity operator, right? So if you write it in the two-dimensional basis, the identity operator takes the form plus, 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 minus, minus. Okay, and we also discussed that Sz can be written to be h bar over 2 times plus, plus, minus, minus, minus. Now notice that both Sz and the identity operator written this way are Hermitian operators. Okay. Now what are the different operators available to us and what other operators can we guess? What other Hermitian operators can we guess in this two-dimensional linear vector space? Well, we can write combinations of this form, plus, plus, minus, minus. In fact, both 1 and Sc are constructed out of these two combinations. But there are also non-Hermitian combinations like this. Okay. Now, our task is, even though this guy and this guy are non-Hermitian, we can judicially construct combinations of these two operators that are indeed Hermitian. Okay. The way I would do it is by starting to symmetrize the operator. So let us consider this particular operator. Okay, plus, minus. By the way, even though these are non-Hermitian operators, they will turn out to be very important in the theory of angular momentum, which we will discuss in the second semester. These are what are called the raising and lowering operators. But for now, let us construct Sx and Sy. So this plus, minus, how do I understand this? How do I understand that this is not Hermitian? Well, let us give this some name. Okay, I'll call this some A plus operator. Okay, now what is A plus dagger? A plus dagger is plus, minus, dagger. Okay, which means I should first switch the order and take the dagger. So this is, oops, minus dagger plus dagger. And the dagger of the bra minus is the ket minus, and the dagger of the ket plus is the bra plus. Okay. So notice that A plus dagger is not equal to A plus, okay, which is the definition of a Hermitian operator. In fact, if I define A minus to be the other guy, minus plus, you can verify that A plus dagger is A minus and vice versa. A minus dagger is A plus. Okay, but even though A plus and A minus are not Hermitian operators, I can construct a Hermitian operator out of them. Okay, how will I do that? Well, let us construct the symmetric combination plus minus, okay, plus minus plus, okay, and I'll multiply this by h bar over 2. The reason I'll multiply this by h bar over 2 is the same reason I've multiplied sz by h bar over 2, because for spin half, the spins are measured in units of h bar over 2. In the case of spin 1, the spins are measured in units of h bar. In the case of spin 3 half, the spins are measured in units of 3 h bar over 2, so on and so forth. H bar is a fundamental unit of angular momentum. And angular momenta are either half integral multiples or integral multiples of h bar. Okay. So what is this combination? Well, can this be a legitimate Hermitian operator? Let's check. I'll first call this Sx, even though I don't know if it's a Hermitian operator. I have to check if it's a Hermitian operator, which you can easily do. The dagger of this operator is h bar over 2. Now the dagger of plus minus, as we discussed, is minus plus. So this would be minus plus. And the dagger of minus plus, as we discussed, is plus minus. So notice that even though the first term itself and the second term itself are not Hermitian, the sum of these two guys is indeed Hermitian, because the second wala is the Hermitian conjugate of the first guy, and the first guy is the Hermitian conjugate of the second guy. So the symmetric combination of these two operators is indeed a Hermitian operator. So I will identify Sx with h bar over 2 times plus minus plus minus plus. Okay. Now what is the other combination that I can construct? Now notice that I cannot add a Hermitian operator and a non-Hermitian operator and construct a Hermitian operator out of that. That is not possible. Why? Because the Hermitian part would be Hermitian by itself, and so the non-Hermitian part will remain non-Hermitian. So we have to construct some combination of two non-Hermitian operators to construct this Hermitian operator. So we are still stuck with the plus minus and the minus plus. So what other combination can I construct? Well, let me try something like, I tried minus plus 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 minus. So let me try minus plus minus plus minus. Would this work? So suppose if I multiply this by h bar over 2. Okay, would this work? Can sy be equal to this? Well, we don't know. We have to first check if this is a Hermitian combination. So let us construct sy dagger. This will be equal to h bar over 2. The Hermitian conjugate of the first guy is the second guy, and the Hermitian conjugate of the second guy is the first guy. And you notice that this is not the same as this. In fact, the second equation is minus of the first equation. So this suggests that if I multiply the entire thing by an I, then the second guy would be a perfectly Hermitian operator, because instead of constructing sy is h bar over 2, if I construct sy is I h bar over 2 times the same thing, minus plus minus plus minus, you can verify for yourself that this is indeed a Hermitian operator, because when I take the Hermitian conjugate, the first one becomes the second one becomes the first one. So there is a relative negative sign between them, but the I outside also becomes a minus I. So the minus I and the the minus one and the minus inside cancel. And so you can prove that sy written this way is actually a Hermitian operator. So these are the other two combinations, in addition to the two combinations that we discussed in class, that we can construct, that we can then identify with Sx and Sy. Of course, you can still ask me, why is this guy Sx and this guy Sy? Can it be the other way around? I don't have a good answer to that question. All I can say is that you can construct two other operators that are properly Hermitian operators out of this combination. One of them I identify with Sx and the other I identify with Sy. Okay, so let me put a box around these equations. because we'll be using them again. So this is my SY. This is my SX. Okay. This is my SZ, and this is my identity operator. Okay. All right. So the next part of this question says, using the operators that you have just deduced or guessed, demonstrate that the combination relation SX/SY is IH bar SZ is true. Okay. How would you do this? Well, let us do it laboriously by actually multiplying it. SX/SY, the combination relation, is multiplying it this way and multiplying it the other way and taking the difference, right? So let me actually do that. So let me actually multiply SX and SY. Now, when I do this multiplication, I will use certain facts. The first fact that I will use is that the plus minus form a complete set. So, excuse me, plus plus equals minus minus equals 1, and plus minus equals minus plus equals 0. This overlap would be 0 because they are orthogonal to each other, right? So let's compute SX/SY. SX/SY. Now SX has a factor of h bar over 2 and SY has a factor of IH bar over 2. So this product has a factor of IH bar square over 4. SX would be plus minus plus minus plus. So let me write it this way. Minus plus 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 minus times SY is minus plus minus plus minus. Okay, I have to multiply these two operators. Remember that the multiplication of two operators gives me a new operator. So let's find out what this operator is. IH bar square over 4 times. Now, so let me do this a little slowly. There is 4 terms here, right? The first term is, so let me multiply the 2 wiggly lines first. Okay, so that I do it one by one and then I show you. So if I multiply the 2 wiggly lines, what do I get? I get minus, plus, minus, plus. Okay, so remember that the bra on the first wiggly line multiplies the ket of the second wiggly line. And the overlap of a bra and a ket is just a number. But this overlap, as we have discussed, is 0 because the overlap of plus minus is 0. So this is equal to 0. Okay. So let me multiply the first wiggly line with the second wiggly line. Okay. What does this give me? Again, this is minus plus, and the second wiggly line has a minus out front. So I should put a minus, plus, minus. So this is equal to the overlap of plus plus is 1. So this is minus this operator. Okay. Now I'm done with these two. So I will multiply this guy with this guy. If I do that, I get plus, minus, minus, plus, and this would be equal to, again, the overlap of minus minus is 1. So this would be equal to plus, plus. And as a last step, I will multiply this with this, and I will get plus, minus, and there is a minus out front, plus, minus, and this would be equal to 0. Okay, those are the 4 terms that you would get if you construct this operator SX/SY. So SX/SY can be written as IH bar square over 4 times, you get 1 factor of plus plus and 1 factor of minus, minus. Okay. So let's calculate Sy Sx. Sy Sx would be equal to, again, there'd be an IH bar square over 4, but this time I had to switch the order of multiplication. So I will do minus plus minus plus minus times minus plus 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 minus. Okay, again I will do it slowly. I'll first multiply this one with this one. I will get minus plus minus plus, and this would be equal to 0 because the overlap of plus minus is 0. So now I'll multiply this with this. So I will get minus plus plus minus, and this would be equal to minus minus because the overlap of plus plus is 1. Okay. So now let me take out these two wiggly lines. And now I'll multiply this guy with this guy. And this will be, there's a minus sign out front. Plus minus, minus plus. So this is equal to minus plus plus. And the last multiplication that I have to do is this and that. So this would be equal to minus plus minus plus minus, and the overlap of minus plus in the middle is equal to 0. So this is 0. Okay. So those are the 4 terms I get out of this multiplication. So I can write Sy Sx, excuse me, as IH bar square over 4 times minus 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 plus plus. So let me now take the difference between these two, Sx Sy minus Sy Sx, which is basically the definition of the commutator of Sx and Sy. This is equal to, both these guys have an IH bar square over 4. So I'll take the IH bar square over 4 out common. The first term is plus plus minus 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 minus. So this is equation 1 and this is equation 2. So I'm doing 1 minus 2. Okay. So if I took minus 2, then the first term would be minus minus minus, and minus of minus is plus. So this is plus this. Okay. So as you can see, there is 2 factors of plus plus and there is 2 factors of minus minus. So I can write this as IH bar square over 2 times plus plus minus minus minus, okay, which I can write as IH bar times H bar over 2 plus plus minus minus minus. And then you go back and look at the representation of Sx and you find that this combination, Sz, which is this combination, plus plus minus minus minus, is basically Sz. So whatever I have here, this stuff is basically Sz. Okay, so this whole thing is basically IH bar Sz. Okay, thus proving the commutation relation that is given to you in the problem. Okay, so let's move on to the second problem. That's the first problem. So let's take a look at the second problem. The result in the previous problem can be easily extended to deduce the commutation relations Sij, sorry, there is a typo there. It should be Sij equals IH bar epsilon ijk sk. Okay, sorry about that. Now consider a state psi that is an eigenkit of both Sz and S square. So remember what we talked about when we talked about commuting operators, they have simultaneous eigenkits, okay? So let us, so S square and Sz can be simultaneously diagonalized. So they have a set of simultaneous eigenkits. So I'm considering an eigenkit of both Sz and S square. Of course, the eigenvalues are different. So psi is an eigenkit of Sz with eigenvalue mh bar, and psi is also an eigenkit of S square with a different eigenvalue, h bar square times S plus 1, whatever that is. For this state psi, compute the expectation values of Sx and Sx square. That is the question. Okay. So I hope the question is clear. The state is an eigenstate of the Sz operator, and for this state we have to calculate the expectation value of Sx and Sx square. Okay, so Sz acting on psi is mh bar times psi, and S square operator, which is, sorry, I'll write it. S square operator acting on psi is h bar square h times S plus 1 acting on psi. S square operator is nothing but Sx square operator plus Sy square operator plus Sz square operator. Okay. Now, how do I figure out? Find psi Sx psi. Okay, that is the question. Okay. So let me start by using one of the commutation relations. So one of the commutation relations is Sy Sz, or let me start by writing the most general commutation relation. Si Sj is I h bar epsilon I j k sk, right? So if I put I equals x and j equals y, I can write Sx Sy is I h bar epsilon 1, 2, 3 is 1. So this is just 1 times Sc. Okay, remember that epsilon 1, 2, 3 equals plus 1. And epsilon 2, 1, 3, if I switch the order, it would be minus 1. So on and so forth. I hope you already know about the epsilon tensor. If not, please ask me later. Now let me take the expectation value of both sides. The left-hand side is an operator, the right-hand side is an operator. So let me sandwich this between a bra psi and a kit psi. So I will take psi Sx Sy psi sorry, I need to find out Sc. So this is not the right commutation relation that I have to look at. Forgive me. What I want is the commutation relation. If I put I equals y and j equals z, I also get the commutation relation Sy Sz equals I h bar epsilon, again y z x y. 2, 3, 1 is also 1. This is equal to Sx. Okay, because I need to figure out the expectation value of Sx. So let me sandwich this between psi and psi. Sy Sz. Again, the right hand side I will sandwich between psi and psi. This is Sx. Okay, the right hand side is what I want to figure out. So let me manipulate the left hand side. What is the left hand side? The left hand side is psi Sy Sc psi minus psi Sz Sy psi. Okay. Now Sz acts on the right on this side to give you mh bar psi. So the first term is basically mh bar psi Sy psi. Okay. Now since Sc is a Hermitian operator, Sc can also act on the left on the bra psi. So this again also gives you mh bar psi Sy psi. But these two terms are exactly equal to each other. So the left hand side is equal to 0. If the left hand side is equal to 0, obviously the right hand side is also equal to 0. So we conclude that the expectation value of the Sx operator in a state which is an eigenstate of Sz is identically equal to 0. Okay, so you can use similar arguments to prove that the expectation value of Sy would also be equal to 0. But the fact that the expectation value of Sx is equal to 0 doesn't necessarily mean that the expectation value of Sx square is also equal to 0. So this is a very important lesson you have to learn, and this is the difference between operators and numbers. If you have the square of a number equal to 0, this means the number is equal to 0 for any real number. But that is not true for operators. Okay? So by symmetry arguments, we can conclude, we want to find out what is Sx square psi Sx square psi. Okay. Now notice that by symmetry arguments, just like the state psi treats Sx and Sy similarly, it should also treat Sx square and Sy squared similarly. So since Sx and Sy should be on a similar footing, by symmetry arguments, we can claim that this expectation value should be the same as this expectation value. What we cannot claim is that this expectation value is 0. We have to figure it out. If it is 0, then it is fine. But just because the expectation value of Sx is equal to 0 doesn't mean necessarily that the expectation value of Sx square is also 0. In fact, it will turn out that this is not equal to 0. Let's figure this out. So what is the expectation value of Sx square? Well, let us start with the definition of S square. S square is Sx square plus Sy square plus Sz square. Okay? Or I can write this as S square minus Sz square equals Sx square plus Sy square. The left-hand side is an operator, the right-hand side is an operator. So let's calculate the expectation value of this operator in the state psi. Psi S square psi minus psi Sz square psi equals, remember that we argued that the expectation value of Sx square and Sz square have to be the same. So I can write the right hand side as twice psi Sx square psi. Okay. And this would tell us what the expectation value of the Sx square operator is, because we know what the expectation value of S square and Sz square are, because psi is an eigenstate of these guys. S square acts on the right to give you h bar square S times S plus 1 psi, and Sz square acting on psi would give you m square h bar square psi. Sz acting on psi is mh bar psi. Okay, Sz square acting on psi would be mh bar Sz acting on psi, and multiplying both sides by Sz on the left. This is mh bar whole square acting on psi. That's all. So the left hand side of this equation, or rather S psi Sx square psi, is 1/2 of the expectation value of S square minus the expectation value of Sz square. This is a shorthand notation for expectation values. So this would be given by 1/2. Expectation value of this guy is h bar square S plus 1 minus m square h bar square. Okay, that is the solution to this problem. The lesson that you learn from this problem is something important about operators, that the expectation value of an operator and the expectation value of the square of the operator are not very simply related. In fact, one is not the square of the other. This is something you should keep in mind. The last problem is rather simple. It deals with the projection operator. For the projection operator Pi, show that the square of the projection operator is the same as the projection operator. And using this fact, what are the eigenvalues of the projection operator? Well, the first part is very easy to show. Pi is II, and remember that I is a normalized eigenstate. So the overlap II is equal to 1. Okay, we're always assuming that we are dealing with orthonormal basis vectors. So what is Pi square? Pi square is II times II. This is equal to I, this multiplies the bra I multiplies the ket I to give you the overlap, right? But again, as we discussed, this guy is just number one. So this is equal to I, which is nothing but the projection operator. Okay, so all projection operators have this property that the square of the projection operator is the same as a projection operator itself. Okay, we can use this property to deduce the eigenvalues of the projection operator. So let me assume that Pi has some eigenvectors lambda and some eigenvalues corresponding to each eigenvector lambda. Okay, all right. So I don't know what the eigenvector lambda is. That is fine. I also don't know what the eigenvalues are, and I need to find out what the eigenvalues are. To find this out, I'll have to use the property that we just discussed, that Pi square is the same as Pi. How do I do that? Well, I'll act both sides of this equation by Pi on the left. So Pi lambda is just a number here. So I can pull this out and act Pi on the ket lambda. Okay. Does this make sense? I hope it does. Okay. Now, what is the left-hand side? The left-hand side is Pi square acting on the ket lambda. But since Pi square is the same as Pi, I can write the left-hand side as Pi acting on lambda. And what is the right-hand side? The right-hand side is lambda acting on Pi lambda, but Pi lambda is lambda acting on lambda. So this is, using the first equation, this can be written as lambda times lambda. Okay? In other words, Pi acting on lambda should be equal to lambda square acting on lambda. But if you look at equations A and B, the left-hand side is the same. So the right-hand side also has to be the same. So we can conclude that lambda square acting on lambda should be the same as lambda acting on lambda. But since the ket is non-zero, this implies that lambda square minus lambda acting on lambda is equal to 0. Since the ket is non-zero, we can only conclude that this part is equal to 0. Okay, that is the only way in which this equation can hold. This implies that lambda times lambda minus 1 is equal to 0, which tells you that the eigenvalue of the projection operator are either 0 or 1 and nothing else. Okay, this fact proceeds from the simple property that the square of the projection operator is the same as the projection operator itself. Okay, so this concludes your tutorial. So I will stop at this point.